So in our opening problem, we are looking at a Venn diagram problem and a continuation of Pythagorean theorem. You're asked to build a Venn diagram for equilateral isosceles and scaling triangles. And so the first question I would ask is, are there any other possible triangles that are not named here when we're talking about side lengths? So for example, is there a fourth side length that's possible? So if you go back to the definitions for chapter 1, there are actually only 3 side lengths that we use for triangles, and those are scaling, isosceles, and equilateral, just as there are also 3 angle names for triangles, and that would be right, acute, and obtuse. So quite often when we do Venn diagrams, we'll draw out circles like this. Sometimes they'll be overlapping, sometimes they may not overlap, but by having these loops like this, what we're implying is that there are shapes out here that don't fit into these groups. And for the triangles themselves, there are only 3 possibilities. So if I try to draw loops that are for these individual triangles, such as, let's say I have a scaling loop and I have an isosceles loop, let's say I have an equilateral loop. If I just draw loops for each of those triangles, what's implied here is that there are other triangles that have side names that don't fit inside these 3 loops. And the truth is there are only 3 names. So there's not a 4th name, which means there's no triangles that would be out here at all. Also, we have to make sure we follow the definition. So for example, if I have an equilateral triangle, which says that all 3 sides are equal, I have isosceles triangles, which are triangles with at least 2 sides equal. Are equilateral triangles considered special isosceles? Well, isosceles by definition is a triangle with at least 2, which means equilateral triangles would fit into that definition because equilateral triangles have at least 2 equal sides. They actually have 3. And all isosceles triangles have to have at least 2. So that means 3 is also a possibility. So for this Venn diagram, for it to be done correctly, because we don't want to have a 4th possibility, what we're going to do is we're going to divide the big loop called triangles into 2 regions. One of them is going to be for scaling triangles, because these are the triangles that have no equal sides. And then on the other side, these are going to be isosceles triangles. These are triangles that have at least 2 equal sides. The third triangle is equilateral, and because an equilateral triangle has always 3 equal sides, and isosceles have at least 2, that means the equilateral triangle is a special case, very similar to a square being a special case for a rectangle, because all squares have 4 right angles, and rectangles by definition is a parallelogram with equal angles or right angles. And a square is also considered to be a special rhombus because all squares fit the definition of a rhombus, which is a parallelogram with 4 equal sides. Well, an equilateral triangle fits the definition of an isosceles triangle because it has at least 2 equal sides. It actually has 3. So we have an isosceles triangle that would look like this, that would not fit inside the equilateral loop. It would have 2 equal sides, where the equilateral triangle, for example, all 3 sides would be marked the same. And for scalene triangles, these are triangles with no equal sides. So that means if we're going to mark the sides, all 3 sides get marked differently. And there are 3 possibilities. So sometimes we will take the entire loop and divide up into the number of sections that we need. and then add in additional special cases if there are any. For the second problem, the Pythagorean theorem, you're asked to find the area of the shapes. That's the squares, and then what is the length of the square that doesn't have any numbers on it. So this is a 13 by 13 square, so that means the area of this is 169. This is a 10 by 10 square, so the area of that's 100, because 10 times 10 is 100. And the biggest square is, if we go back to the sketch we did last week, we would take these two areas and add them together, because the bigger square is made up of the pieces from the two smaller squares, if the triangle region that we're starting with here is a right triangle. Here we have a 15 by 15 square, which is 225. The biggest square is a 25 by 25, so that area is 625. 25 times 25. And then this area here is 400. Because if I take the 625, which is the biggest square, and I get 225 to this square, then this square gets what's left, which is 400. Now Pythagoras is given credit for developing a number system because during this time the number of triangles that were being used were very limited. And what I mean by limited is that the lengths themselves had to be whole numbers. And what Pythagoras is trying to explore is, can we come up with a way of defining areas of squares when the numbers are not really nice numbers. And so he came up with a whole new number system called square roots. So he decided to use squares because he understood that only one square has an area of 4, and that's a 2 by 2 square. And if I was looking at an area of 9, for example, there's only one square with an area of 9, and that would be a 3 by 3. And he understood that every square has a unique area. So he decided to name the length of a square based on the area. So the length of this square here would be the square root of 269. So he decided to use the area as the number with the symbol called square root. Now square root by definition is basically the square's length. So it's the square's length with an area of 269. So that would be the length of each side of the square. This one here would be the square root of 400. Now sometimes, when we put these in the calculator, these square roots, sometimes they will give us a really long decimal number, which this one does. So we leave it to the square root of 269. And sometimes they will give us a really nice answer, and this one does. So the square root of 400 is 20. So if you have any questions about these problems, please ask when we meet next.